Today we will discuss a bit the results of my my latest paper about the characterization of deep proton implants in silicon. So it's not written here in the title. Deep proton implants in silicon, they are characterized by dynamic SIMS. Then I will show basically some collection of depth profiles of hydrogen implanted silicon. If you are interested, most of the data I will show you today are taken from this paper that was published in February. And this work is part of, it comes from a collaboration between the University of Catania, where I'm placed, and ST Microelectronics. It's a quite big company in the famous in semiconductor industry, manufacturing, and the University of Oslo, where I performed all the characterization, and as the moderator said, where I spent around 1 year in doing research. This work is also part of my PhD project. Just 2 words about this. My PhD project is about the characterization of channeling proton implants in silicon carbide. Then this work is just one of the 3 steps of my project, where the final goal was to analyze this kind of implants. But let's go to the point. And before showing you, of course, before showing you my results, I would like to give you some background about the importance of analyzing hydrogen in the semiconductor industry. Then we'll just see more about hydrogen in semiconductors. Then I will say some word about the importance of proton implantation. Then we will move to the problem itself. I mean, the hydrogen detection, all the techniques you can use, and so on. And we will focus at the end on the profiling by dynamic SIMS. Then we will see my results. Now, I think that many of you are familiar with semiconductors, maybe because you are joining this webinar. And then what about hydrogen in semiconductors? The hydrogen is it's a really abundant element that you can find in perhaps in every step of semiconductor manufacturing, starting from the beginning. I mean, from the growth of semiconductor materials, because I think, as you know, most of the deposition techniques used to grow thin layers of semiconductors uses precursors that contain hydrogen, basically. Another source of hydrogen contamination or incorporation, no, it depends on it's the post-growth processing, where I mean processing of the material itself, or the ultimate devices. Then with processing, we have a lot of sources of contamination, mainly surface and subsurface contamination, like etching treatments, plasma and thermal annealing treatment, and other treatment, like, for example, all the operations related to photolithography, like covering with masking with resist and so on. But you can also incorporate hydrogen by proton implantation, and this is something you do intentionally, basically. Proton implantation, there has been found to be quite useful in semiconductor manufacturing or power device engineering. And here I just put some example of the application of proton implantation. So here you can see I just put silicon carbide, 3,5 compounds, silicon, and dielectric. Now, what we know about the effects of proton implantation is that it can be used to create doping into the material, even though the hydrogen itself it's not dopant. But so as you can see in this in this graph here, where we have the energy of different semiconductor compounds, and so this line here is the formation energy of the neutral hydrogen interstitial, and depending on where this formation energy level lies, the species can act as a p-type dopant or n-type dopant. Another effect of the proton implantation is the passivation of traps. Passivation or creation of traps. There is what they use for silicon technology, but also for silicon carbide. The uses in silicon technology are basically actually are quite old, and so the object of my study I will show you is a structure that is commonly used in manufacturing of bipolar devices based on silicon. Then there are also other applications with minor application, like wafer slicing, where they implant a really high dose of hydrogen, and by heating they produce bubbles of hydrogen and slice the wafer. So the interest in using protons, other than the effects, the application, is the penetration depth of this species. So here, for example, we see 3 different species. Phosphorus and nitrogen are common n-type dopant, and the hydrogen. As you can see, with the same energy, you can implant this species so much deeper than heavier species with a low degree of irradiation-induced damage. There is really important for this kind of application. Then you can definitely use hydrogen to create buried layers of of implanted regions. And this is an example of proton implants in silicon. So here I'm showing you a spreading resistance profile. There is basically an electrical measurement which measures the carrier concentration. And this structure here, there is called a multi-energy implant or a multiple implant. It's basically made by implanting several energies. And this is used, but it has been used for at least 20 years for as buffer layer for bipolar devices, like insulated gate bipolar transistors made of silicon. And you can remember this, take a picture of this graph, because this is the object of of my work. What is really important in this with hydrogen is that so if you can measure the electrical properties produced by the proton implantation, you also need a complementary mean to give a sense to these measurements. And the complementary mean should be a technique able to detect the hydrogen. Then we are talking about elemental analysis. There are several techniques that can be used to analyze hydrogen. So here, for example, I put there are like 10 different techniques capable to detect hydrogen. And so as you can see here, I divided these techniques into bulk techniques, which give information on, which can give quantitative information on hydrogen concentration and other features like chemical bonding and so on. But these techniques are not suited to make profiles. So you don't have basically a depth resolution. While you have a series of other techniques that can be used for depth profiling. And we can divide these in ion beam techniques and electrical techniques. With the ion beam techniques, you can basically detect the hydrogen itself, while with so using electrical techniques, you basically have information on the electrical properties that can be related to the presence of hydrogen, but also not. Then, of course, you need to correlate both measurements to make further studies. And here I just put some example of these techniques. One of the most famous, of course, is the so-called ERDA, or elastic recoil detection analysis. So I think that some of you know that this technique is a variation of the Rutherford backscattering spectroscopy, and it can be used to detect hydrogen. Even though this technique is powerful from one point of view, because from this measurement, from this technique, you can obtain the absolute hydrogen concentration in atomic percent. That if you know the density of the material, you can convert it in, for example, in atoms or centimeter cube. And then this is a good point to use this technique. But on the other side, if you are going to analyze low-dose implants or deep implants, this is not really suited because the dynamic range is quite short. So both in terms of probing depth, because with this technique, you can probe no more than 1 or 2 microns, depending on the energy of the ion beam. And also you have some limitation in terms of limit of detection, because with the ERDA, for example, the limit of detection is is like 0.1% atomic percent. That for hydrogen in silicon, for example, it means something like 1 × 10⁻¹9 atoms or centimeter cube. There is actually a concentration related to a high dose implantation. Then this technique is quite limited for our purpose. I mean, similar story for the nuclear reaction analysis. It's another technique. It's quite similar to the ERDA in terms of limitation, let me say. And these are basically the two options with ion beam techniques, other than the SIMS, but we will discuss it later. I just tell something about the the electrical techniques. This is what I just showed you before, the spreading resistance profile. I think this is the this is the most powerful technique for this kind of analysis, because the probing depth is it's basically unlimited, and you also have a really wide dynamic range in terms of, in this case, charge carrier concentration. So you can span over 6 or 7 order of magnitude. And this is why the spreading resistance is commonly used to characterize these kind of structures at the industrial level. But you can obtain depth profiles also with with other techniques. Another famous technique is based on the capacitance voltage measurement. So here, for example, we have a doping profile. This is my measurement. It's a doping profile of 400 keV protons in silicon after thermal activation. And the limit of this technique is the probing depth and concentration dynamic range. There is quite limited compared to the spreading resistance, of course. The last technique I showed you is the DLTS, if anyone have ever heard about this. is the deep level transient spectroscopy. It's still a capacitance technique, but that gives you the possibility of extracting the defects profile. Really powerful and really useful, but with same limitations of the CV. But we have not yet told nothing about the SIMS. What about the SIMS? The SIMS, of course, it stands out as the most powerful technique among the ones I showed you. But you know it, of course, because with SIMS you have a really wide dynamic range. You can play a lot with detection limit by adjusting the parameters, like the sputtering parameters and so on. And you have virtually unlimited probing depth. Why I say virtually, we will see. There is also some limitation in using SIMS for the analysis of hydrogen. And so basically you have three main limitations. There are the source, because to analyze hydrogen, you need cesium to extract the hydride ions. And another big problem is the high level of background for hydrogen, because you have contamination from everywhere when you analyze hydrogen. And also, third, if you are going to analyze really deep implants, you should consider time issues and also other issues that we will see. Then we have basically two questions with this kind of analysis. What is the detection limit I can reach by using, so here I said, by using a non-dedicated instrument, because this, of course, these measurements are carried out, but with a dedicated instrument. With dedicated, I mean that they are used only for the analysis of hydrogen. So they are instruments where the presence of contaminants is really minimized. Second question is, how much deep can we measure? Because of course we have to consider that the probing depth is in the reality is not unlimited at all. These two questions are related to two really famous issues of dynamic SIMS. The first is, I think you know, is what is called the depth profiling issue. Because you know, so let me see if I can take the laser. So when you when you perform a dynamic SIMS measurement, what you do is to, so if the laser is the beam spot, you raster the beam over a given area. Then you, through the optical and electronic gating, you choose a little region in the center where you decide to extract the secondary ions. And the condition that must be satisfied to have the best depth resolution is that this little region here corresponds to a region of the crater where the bottom is flat. The more flat is the bottom, the best is the depth resolution. And when you start losing this condition, then when the analyzed regions start covering the walls of the crater, you can experience this effect here. It's like a tailing of the profile. It's the dashed line. And this is what is called the crater edge effect. Then, of course, you want to avoid this effect to obtain a real true profile without artifacts. The problem with the crater edge effect is that it becomes more likely, more probable during the sputtering process, because the deeper you go, the higher is the probability of experiencing this effect. Here, for example, I'm showing you some profilometry measurements. These are still my measurements. So here we have 4 different craters made in silicon. my samples, 4 different craters with different depth. And in the inset, I put so the ordinate is the standard deviation of the depth of the bottom, considering a little area of 33 times 33 micron square. Then is the standard deviation against the depth. As you can see, the the error on the depth of the bottom increases more than linearly with the depth. Then if you are using, for example, a raster size of 200 microns and you are analyzing an area of 30 microns, at some point you will not be able anymore to keep the flat bottom condition, and you will see the crater edge effect. The other issue is related to the contamination of hydrogen, because as you know, so when you work in vacuum, perhaps the most abundant species are water and molecular hydrogen, and these represent a source of contamination where we are going to analyze hydrogen. If to this you also add the contamination of surface, like hydrocarbons coming from so simply from dirt or just from absorption from the atmosphere. And if you also consider other effects like matrix related effects, you have that basically you have that the hydrogen is the species with the highest level of background, and this make it really difficult to analyze low dose implants, for example. I mean low concentration, because so if the background is higher, it's probable that the noise is quite high and the detection limit is low. To minimize this effect of the background, then to reduce the effects of hydrogen contamination, it has been proposed recently a protocol that involved the use of the cesium source to reduce the background level. And this protocol is called prespattering or cesium prespattering, it depends. And so basically it consists of irradiating the sample before the analysis with a high current cesium for a certain time. And what they observe, so here, for example, I'm showing you 2 different works. This is for this is from 2006, and the other one below is really recent, is from the last year, 23. Then in these works, the authors observed that if you irradiate the sample with cesium, then with the same source you are going to use to make the analysis, you can observe a decreasing of the background level for different species. So here, for example, we are looking at 3 different materials. So here it's silicon, in the middle it's gallium arsenide, and this should be indium phosphide, if I remember correct. Anyway, in any case, then it's independent of the material. The effect of irradiating with cesium with this so-called prespattering protocol is to reduce the background of several atmospheric species and also the hydrogen. Same story, similar study was made in this more recent paper from 23, where where the authors analyzed some atmospheric species in silicon. So here we have hydrogen, carbon, and oxygen. And in these graphs, you can see the detection limit against the sputtering rate. So as you know, it should be that the higher the sputtering rate, the lowest the detection limit, because so in the same integration time, you collect more ions. And so here, what they observe is that is a quite large difference between the measurement without using the presputtering and the measurement carried out, obtained with using the presputtering. So here, if you just focus on the hydrogen, we have a lowering of almost 1 order of magnitude. And what they say is that we can reach detection limit around 1 to 10 to the 16 atoms over centimeter cube. Then basically, so here I'm showing again the same story, the effect of presputtering, but these are my measurements. So here on the left, you can see this is the signal of hydrogen. It's the bare signal, the counts per second, against the presputtering time. So as you can see, the signal goes lower and lower, and at some point you reach a kind of plateau. It means that the signal becomes more or less stable. It's not really true, but at some point the rate of lowering is so low that you cannot observe any lowering. And these are the results if you take the measurement at different times after the irradiation. So here, the first measurement, for example, after just 2 hours of irradiation, it's not a good measurement because you have so you have a quite high background and the baseline is not straight. Then you have to, if you want to take something from this measurement, you have to subtract the baseline and so on. After some hours, for example, 8 hours, when we reach the plateau, you can obtain this really nice profile with almost constant background, and basically where the signal to noise ratio is really high, and you can aspire to obtain a low detection limit. And this is actually what I made in my study. Now I will show quickly all the depth profiles I measured on these samples. So for this study, I used 8 inches or 200 millimeters N-type silicon wafers given and implanted at ST Microelectronics. And these samples are implanted with single implants with 4 different energies, 400, 800, and so on. And one wafer is implanted in the multi-energy mode. There is basically a sequential implantation from the highest energy to the lowest. Then you have 4 peaks implanted into the same materials. The measurements were taken with this instrument. I think that some of you should have used this at some point. Is the Kameka IMS-7F. So as you know, is a really performant instrument for the profiling of inorganic materials. And work was basically, so it basically consists of an optimization of parameters in order to obtain the best measurement. Then what I did here was basically to try to improve the signal to noise ratio by working on the primary ion beam current and the sputtering conditions. Then, I mean, the raster sides and also the optical gating and so on. And secondly, I tried second, in parallel, I try to minimize the crater edge effect, because when you analyze a really high energy implant, you go to you analyze depth of 10 or 20 microns. Then it's quite easy to see this crater edge effect. And of course, we also applied this pre-sputtering protocol to try to reduce the background level for hydrogen. At the end, we tried to find a compromise between depth resolution and analysis time, because of course it's a quite long measurement. So here briefly I put these two tables. So these are taken from the paper, but it's just to show you what are the parameters I've worked on. So here, for example, in table 1, you can see, so I put initial conditions and optimized conditions. And here I put some parameters of interest. So as you know, you have a lot of parameters you can adjust during the SIMS measurement, but there is something that is more frequent, that you adjust more frequently. For example, the primary ion beam current or intensity, the raster size, but also the analyzed area. And the other parameters I played on is the contrast aperture. And here the green values are the values of the optimized conditions. So here the work was basically to try to increase the current to increase the signal, increase the raster size by keeping constant the analyzed area to reduce the crater edge effect. And at the end, increase the contrast aperture to recover some signal, because the contrast aperture is proportional to the number of secondary ions that you send to the detector. Then you increase the numbers of secondary ions. Then you decrease it a bit, because when you increase the raster size, the sputter rate goes down. And at the end, you try to recover some signal by adjusting the contrast apertures. And these are the results, table 2. So here, what I can say to you is that with a measurement that takes only around 2 hours, you can obtain a limit of detection of 3 times 10 to 16. Where here, and I want to underline this aspect. Here, the detection limit is the classical definition of the detection limit. There is basically 3 times the noise. And then you have this really low detection limit, a depth resolution of 20 nanometers. That is quite good for the depth we are analyzing. And in the same measurement, we are able to almost kill the crater edge effect. And now I will show you these measurements. So in this graph, for example, I put the measurements taken with the initial conditions, then it's the red curve. And it represents perhaps our first attempt, or one of the first trials we made. The black curve is the optimized measurement. And at the end, I put this green curve. There is the optimized measurement plus the pre-sputtering, then plus using the pre-sputtering protocol we discussed a bit before. And so the dashed lines are the SRAM simulations. Now, what you can see here is, so I think it's quite clear that with the initial conditions, you have a really high noise, and this is clear. But you also have a really pronounced crater edge effect that you can see in this tailing here. Then with the initial conditions, you have the crater-edge effect, basically. And the third thing you can notice is that we are not able at all to detect the low dose peaks. There are these two peaks. Then now, if you consider that, for example, this peak here is between 1 and 2 times 10 to 17, and this is basically something we cannot see with these conditions. And if we go back to the previous slide, that's basically what the LOD we calculated for the initial, we measure for the initial condition is basically 2 times 10 to 17. Then if we go lower, we cannot see anything. Better results by using the optimized conditions, where we are definitely able to detect all the 4 implants, because you can also see something here and here. We are also able to minimize the crater-edge effect. But there is still another issue. It's the background. So the background changes. Then, of course, so if you are going to use this measurement for repeatability or reproducibility purposes, it's not really good, because you have to perform an operation, a mathematical operation on this measurement. That is to subtract the background. If you also add the pre-sputtering procedure, you have this green profile. There's let me say, I think it's perfect. We can see it's perfect compared to the other 2 profiles. Then we can tell definitely that the pre-sputtering enable the detection of all the implants, and make it possible to use the measurement without correction of the baseline. What is interesting here is that with the pre-sputtering, we don't change so much the limit of detection. Then the limit of detection, you have to keep in mind, is primarily controlled by these parameters here. So with the pre-sputtering, you just have the constant baseline. Then of course it's good, because you avoid further modification of the data. And of course, after the optimization, I did a lot of measurements to test the repeatability of this measurement here. And in this graph, for example, you can see the single implants. As I said before, it's 400, 800, 1000, and 1200 kV implants. And with the result that the measurement is, so the repeatability is really high, because, so I didn't put numbers here, but I calculated that the standard deviation on the peak position, for example, is around 20 nanometers. So it's basically the same as the depth resolution. So if you are asking why I put this measurement here, this is the one I showed you before. It's just to remember what is the effect of the cesium pre-sputtering. Same repeatability test I did for the multi-energy implant with almost the same results. Then you have to consider that these measurements so they take like 2 hours for each measurement. Then it's quite it's a lot of time spent with the cesium source. And so if you have ever used the cesium source, you can so you know that it's quite difficult to keep the cesium source stable for a long time, and of course when you are using a really high current, because differently from the liquid sources like oxygen, for example. If with oxygen you can reach a current of 600 nanoamperes or more. With cesium you cannot go you cannot go more than 300 nanoamperes because it starts defocusing at some point. Then it was not really easy to take this measurement, but you can do it. Another graph I want to show is this. So this is just a comparison between the multi-energy implant, it's the blue curve, the blue profile, and the single implants, the red. So here the implants, the baseline, of course, it's cut for clarity, just for clarity. And so this comparative graph here is really useful when, so this is just for your information. It's really useful when you are testing a multi-energy ion implanting system. Because in this kind of system, what you do is to implant sequentially different energies. But between one implant and the next, you change the energy. And if you know, when you change the energy of the beam, it takes some minutes to stabilize. Then such a measurement is quite useful to test if the machine is working correctly. Because if the beam is stable during the multi-energy implantation, you should see that the peaks are superimposed with the single energy implants. And this is the case. So in this case, we can see that the machine we used was working good at the time of the implantation, of course. The last graph I show you is this. I think it's perhaps is the most useful application of this kind of analysis. There is it's basically the coupling or combination between the SIMS and the electrical profile technique. There is basically the the spreading resistance profiling. So coupling these two measurements is really important where we are going to study to perform material studies. That means studies that are not finalized to the characterization of the device itself. But so here we are going to study the material properties. So for example, if you want to find the correlation between the electrical profile and the ion implantation profile, of course it's needed to have such a measurement. There is basically the SIMS measurement. So these profiles here are, so it's quite nice to see that for this kind of structures, there is proton implanted silicon. These profiles follow basically the defect distribution. So here you can see the electrical profile is the same as the defect distribution. This is just a simulation. And of course the same is for the SIMS profile that follow the ion range or the ion distribution. And so I repeat it. This is the most useful application. This is the reason why you should use you should be able to use SIMS for detecting, for analyzing hydrogen. And so with these results, I just go to the conclusion that it's quite clear. So we found, we adjusted more than applied the protocol, already existing protocol. We adjusted it to measure this particular structure here with the results of obtaining a detection limit of 3 × 10⁻16 atoms per centimeter cube. That for silicon, for hydrogen in silicon, it means around 600 atomic part per billion. And with these conditions, we can tell for sure that we are able to analyze beyond 20 microns in depth. So here I can tell you that with these conditions, of course, and with these conditions, I mean with these raster size and analyzed area, So I started to see some problem, some tailing around 30 microns. Then if you go to 30 microns, I think you have to change a bit more the parameters. And then we obtain this measurement with a good depth resolution, 20 nanometers. Then 20 nanometers on 20 microns, it's 1,000. It's around 0.1%. Then it's a good relative depth resolution. And the last thing I want to say, and I hope it could be useful for some question, is that so after these measurements, after this optimization, I estimated that by changing some parameters and using the max raster size for this instrument, for the Cameca IMS7F, there is basically 500 microns. We can reach, theoretically, ideally, we can reach a detection limit of 5 times 10 to 15. There is something like 6 times less, 6 times lower than what I showed here. And that's all. For this work, of course, I want to, I need to say thank you to ST Microelectronics for the resources, for the wafers, of course, and for the ion implantation that is performed in the ST Microelectronics site of Catania, Sicily. And thank you also to the Research Council of Norway and to the University of Oslo for the availability of the SIMS, basically.